more of this. Kind of doing what we can in this hour. Concavity is the slope of the slope. The information comes from the second derivative. Concave up means a couple things. F double prime of x is greater than 0. So I'm just saying a positive second derivative. Concave up means your slope is getting bigger. It doesn't have to be positive or negative either, but it has to be increasing. Concave up is nice because the U is exactly what concave up looks like. So concave up can either look like that, which is actually an increasing slope. So if you look at that, if I were doing the surfboard thing, like your slope right there is really negative, right? As I go along, doesn't it get less negative? Less negative, less negative, 0. So like if your bank account went from really negative to less negative to less negative to less negative to 0, that's increasing, right? So this is a negative slope that is increasing. So the fact that it looks like part of a U is the easiest way to remember it. That's concave up, but it's curving up. So it could also be this. Anything that is curving upward, whether it's on the way down or on the way up, is concave up. It also means, so if you look at it this way, slope is increasing. Which means f prime of x is increasing. How do you feel so far?
Makes sense,
Okay.
but I just feel like it's going to be really confusing.
Are you with me so far? Yeah. Okay. Can we do the concave down notes? You guys can do it yourself, basically, right? So concave down, if you write the n like a lowercase n, but write it gigantically, that's what concave down looks like. It's the other version. So your derivative in this case would be negative. Your second derivative would be negative. It's going to be either that part or that part, but it's curving down. And it means your slope is decreasing. Or f prime of x is decreasing. So f double prime of x greater than 0. What's that mean?
F prime of x is...
I can handle that. What's next? Increasing. Good. And what's f of x?
Positive.
Second derivative positive means f of x is... Yes. Those three are all the same statement. I'll leave that on the board so we can make reference to it for a little while. Second derivative positive means your derivative is increasing. That just means your slope is getting bigger as you go. It means you're curving upward. That's concave up. So then the opposite, so second derivative less than 0 be f prime of x decreasing equals f of x concave down. Concave just means curving. Like you're just curving up or you're curving down. Okay. This is f of x. So this is the original graph. So because I can start from any level eventually, first derivative or second derivative. So here we're starting with the original graph. Where is f of x increasing? Well, wouldn't it be like from negative infinity to b? And then from where else to where else? D to positive infinity. So that's just like, what does increasing mean? It just means positive stuff. Where is it decreasing? There's only one interval. From where to where? B to D. Relative max at x equals what? B. Relative min at x equals D. You with me there? I'm going to actually draw the first derivative for you so you can hopefully see how they relate a little bit. Your first derivative look like that. This is B, and this is D. So if you notice, when f of x is increasing, where is your derivative graph? So f of x is increasing from negative infinity to b, and from d to infinity. It's positive, right? It's above the derivative graph would be above the axis. When the derivative graph is above the axis, this has a positive slope. So even if I put it up here, when the derivative is above the axis, your original has a positive slope. When your derivative is below the axis, your original has a negative slope. And then back here, we're back to derivative here, above the axis, and we've got a positive slope. This is a relative max on the original. That's how a relative max looks at a derivative, because the derivative went from positive to negative. Relative min right here, that's how a relative min looks on a derivative. It went from below the axis to above. How we doing? There's a lot. I'm throwing a lot at you. So I'm trying to like scratch the surface of like 5 different things in order to hopefully get you far enough that the con helps you. So let's go to concavity. I'm just going to erase that. Alright, where is f of x? Concave up, concave down, and then where are there points of inflection, which I'll talk about in a second. So concavity is either, the graph is always, I don't know, it's lying against this picture. Graphs are typically either curving up or curving down. It's just a combination of like U's and N's and U's and N's. Can you see how this graph is basically an N connected to a U? Like that's all that graph is. So concave down is when we're curving downwards. We are curving downwards the entire time until we get to, and it's hard to tell exactly just on a graph, but like somewhere around there, I tried to make it right at C. Do you agree that we're curving down up until C and then curving up after that? That's what it's going for. So curving down is concave which? Curving down is concave down. So we're concave down from negative infinity to C. And concave up from C to infinity. So we got the big down part, and then we switch, and now we're curving up. Point of inflection is just where it changes from one to the other. So that's at C. Questions there? You're good? Should I stop?
Don't erase the right side.
I just realized when recording, nobody can see that marker.
Oh well.
Sorry,
That's
Steve.
what I realized you were teaching side better.
Sorry, Steve.
It's okay, they'll figure it out from the words.
Don't do that. That's too much.
Thank you.
Just copying it out would take 5 minutes. So we'll just do like a W.
Have a little bit in front of the axis.
It's supposed to be a little in front of the axis, yeah. So now I'm going by numbers. This is f of x. Is it easier to see if I put paper behind it?
Yeah, it's very separated.
Try those. You're going to be rounding a little because my graph's not like perfectly placed, you know. But no, I wasn't even looking at them. I don't look there. I was just so when I look at this, I see up to like there, down to maybe there, and then up the rest of the way. Fair enough? This is kind of debatable. Like that could be a -1, that could be a 0. It's somewhere in there it switches though, right? Somewhere around there. So concave up, I'm going to say negative infinity to -3. But if you were like, no, I think it's -3.5. I mean, that's fair enough. Then I'm going to say like 0.5 to exactly the right place in the numbers. But you see my point? Like that's where it's curving up. And then this part in here is where it's curving down. So like -3 to -0.5 based around. I'm sorry. This should be -0.5. Yeah. So then based on my numbers, which yours might be slightly different, I get that, but based on my numbers, where are the points of inflection? Careful. Oh yeah, you're okay. You can say that. -3 and -0.5. I forgot this was an original graph. If you have like a derivative graph, you can't give me the y coordinate because you don't really know. But this was good. I'm gonna add that or something like really close to that. Questions on it? Okay, take out that sheet I gave you. Let's start doing some problems. You're not gonna check homework. Nobody got time for that. Hey, did somebody forget the Walmart is yours? This okay. It was in Diaz. That's what you got. Someone like brought it up. I thought Diaz had it.
It's on the
Are you okay just for you?
Right now?
Yeah, how are you doing?
I'm stressed.
No, you seem less stressed.
I'm getting there. Still stressed though.
It's really crazy.
Not to talk about your stress level on the camera.
It's okay.
Let's not break the deal.
Okay.
Anybody get extra?
Stop.
You gave me and Gina the papers, and that was it.
You gave our
No, I gave that. I should have. There should have been 2 extras in this row,
Still with Julia.
but I didn't give Julia. I only gave you 2. I thought I gave you 3.
Julia was up and about. Wrong piles.
Yeah, you're busy messing up my file.
Maybe that's why she put this stuff in the wrong piles, because she didn't get rid
She didn't know that yet. Okay. We are going to do the increasing, decreasing, relative max, relative min portion first. So to get to the second derivative, we got to take the first derivative, right? So while we're doing the first derivative, we're going to review on this problem, like yesterday's homework. So review increasing, decreasing, relative max, relative min. And then basically we repeat that same process for the second derivative. And that same process for the second derivative will tell us concave up, concave down, and points of inflection. So you already learned the process. We're just applying it to a second derivative instead of the first. So you'll see what I mean when we keep going. So the first derivative, r prime, we bring down the 2/3, so it's -2/3. 4x minus 8, reduce the power by 1, multiply by the derivative of the inside. So if I rewrite that, it'll be -8 over 3 times 4x minus 8 to the to the positive 1/3. Keep this like try to make 2 columns. That's what we're going to try to first derivative here, second derivative here. What do I do with the derivative? I heard set equal to 0, but I need more than that. So the top and bottom equal to 0, right? So the top being set equal to 0 is useless. In this case. The bottom being set equal to 0, that's really just 4x minus 8 equals 0. Because if I undid the 1/3 power, 0 would say 0. If I divided both sides by 3, the 0 would say 0. So basically that crap doesn't matter when you're set equal to 0. So what's x equal? So x equals 2. So we got a giant number line with 2 in the middle. How many intervals do we have? 2 of them. -infinity to 2. 2 to infinity. Go ahead and plug in. Where are you plugging into?
B.
I'll probably pick 0. Plugging into the derivative, which is this fellow here. 0 minus 8 is a negative number. Third root of 8, positive or negative? Negative. To the first power? Still negative. Times 3? Still negative. And then I have a negative divided by negative. So this means f prime of x is positive, and f of x is therefore increasing. Do the same thing with, I don't know, let's say 10. 4 times 10 minus 8, that's a positive number, right? Third root of a positive number? Still positive to the first power. Still positive times 3. Still positive, negative divided by a positive. So the derivative is negative, which means f of x is decreasing. Do we have a relative max or a relative min?
Yes.
Which one? Relative max or local max at x equals 2. Because that's where we switched. That was last night's homework, right? That's the exact process you did. We're going to do the exact same process, just with the second derivative instead of the first. If it comes out positive, it'll be concave up. If it's negative, it'll be concave down. If it changes, it'll be a point of inflection. It's the exact same process. So my derivative, I think that I would rewrite this by bringing that back up. You see what I did to get to that? Because I don't want to do close rule if I can avoid it, so I'm just going to bring it up. So the negative 8/3 stayed there. This guy popped up and becomes a negative x. Now take the derivative of that. So negative 1/3 times negative 8/3 is a positive 8/9 times 4x minus 8. So what power now? Negative 4/3 times what? 4. Simplify that. So on top, 32. On the bottom, I have 9 times 4x minus 8. So 4/3. With me? Exact same process. So we set the top and the bottom equal to 0. So if I set the top equal to 0, 32 equals 0. It's garbage, never happens. Set the bottom equal to 0. Let's say we divided both sides by 9. Well, 0 is still 0. Let's say we raise both sides to 3/4 power. That cancels 0 is still 0. So what's x equal? X equals 2. What?
Will always be the same.
No. It can be. It doesn't have to. It'll be a mix. Like sometimes it will, sometimes it won't. So these will not always necessarily be the same number. They'll often. Sometimes there's 3 numbers, 2 of them are the same, 1 is the same. I mean, it could be, it could not. Same idea. We have a giant number line with 2 in the middle. How many intervals? 3. Or 2, sorry. Negative infinity to 2. 2 to infinity. What if I was just thinking that's 3? And then thought, like, trying to carry out the goes.
You mess us all up. We're already in a hurry, so that wouldn't be good.
So now, it's the same process, but we're doing it with the second derivative. I'm trying to find out concavity information. What levels does concavity come from? Original, first derivative, or second derivative? Second derivative. So when I pick a point and plug back in, where am I going to plug into? Second derivative. So if you plug it back into the original, what are you finding? Y values. If you plug into the derivative, what are you finding? Slope. If you plug into the second derivative, what are you finding? Concavity. That's calculus. Like, that's like the main, right there was like the main thing you should get from this class. Because
Say that one more time.
if you plug into the original function, what do you get? Original function. Y values. If you plug into the derivative, what do you get? Slope. If you plug into concavity, what do you get?
Second derivative.
You're gonna need to say it a third time.
If you plug into the second derivative, what do you get? Concavity. What's your question?
Is there anything that has to do with the third derivative?
The third derivative is So if you look at it in physics terms, original is position. What's change in position? Velocity. That's the first derivative. What's change in velocity? Acceleration. That's your second derivative. Change in acceleration is called jerk. That's the third derivative. That's like I'm accelerating, but they say jerk is what spills your coffee when you're driving. So like you're like jerking back and forth because you accelerate and slow down. You know the buses in this district, they like floor it and then take their foot all the way off.
Absolutely.
That's jerk.
My bus teacher used to stop so fast my head hit the ceiling. Also,
Fascinating story. Thank you.
it's true.
So that's the third derivative.
Planes spot or something.
Oh yeah, I could have gone with that too. So, come back. Still going here. I'm gonna pick a representative point. Say 0. Plug it into where? Second derivative, because I'm looking to find out about concavity. Plug 0 in here. What's 0 minus 8? I don't care about the number. Negative. Third root of a negative. Negative. To the fourth power. Positive. Times a positive? Positive. Positive divided by positive. It's positive. So second derivative is positive, which means f of x is concave up. That is like the main point I'm trying to get to today. All the stuff we've been doing is to get to that. Same thing here, plug in like 10. It's not going to matter, right? It doesn't matter what I plug in. Because that fourth power is going to change anything I put in there to what? To positive. So do you want me to run through the 10 again, or can I just say positive? Alright. So over here, your second derivative is also positive. You are also concave up. So, is there a point of inflection? Point of inflection is when it changes from up to down or down to up. Is there one? No, because it didn't switch. I want to start you looking at what we're doing too. Like we're headed toward this, but again, I'm giving you small pieces of things along the way. If I asked you if this was increasing or decreasing here, what would you say? Increasing. Concave up or concave down? Concave up. Well, didn't we just find that from negative infinity to 2, we're increasing and concave up? You see how that matches up with the graph? Eventually, what we're getting to is, here's the information, you make the graph. So you're going to have to look at it and be like, okay, from here to here, it's increasing in concave up. From here to here, it's decreasing in concave up. From here to here, et cetera, et cetera. That's where we're headed. You don't have to do that yet. So now I'm just going to say no, point of inflection, and I'm going to move on. POI, point of inflection. Person of interest. Find another one that looks hard. You want 2?
Oh yeah, do 4.
4, 7.
Let's do 4.
10. The fractions. Scary, very scary fractions.
You guys will be okay. So, when we start graphing them all, you can't forget about all the stuff we learned before. Is there a horizontal asymptote? Okay, that you can see it. Why is there a horizontal asymptote at 3? At y equals 3. What's true about the highest powers? They're tied, so then you look at the coefficients, which gives you 3. Right? Why is there a vertical asymptote at x equals 1? So when the bottom equals 0. And the bottom equals 0 and what?
It doesn't cancel with the top.
Yes, because if the top equals 0 also, if you get 0 over 0, what's that? Indeterminate, which looks like what on a graph? A hole. 0 over 0 is a hole. Anything else over 0 is a vertical asymptote. Again, it's like, I feel like this is calculus on speed or something. Let's take the first derivatives. I am not going to use s's because I'll think they're 5's and I'll screw it up, so I'm going to change them to x's. That's what I'm going for. You don't have to call me that.
Everybody makes a little bit of that.
first derivative?
I have a question.
Yeah.
What do you do with, like, top? We actually have to set it equal to 0 and solve. I just like another.
It would just like tack on another critical point. Yeah, because none of these recently have had that.
None of our
No, I think the very first one we did. Really want to fight for me. Alright.
At least, like, none of those are different from working.
Oh, really?
Yeah.
Oh, okay. Okay. Set the top and bottom equal to 0. So the top can definitely produce critical points sometimes. It just hasn't happened to in any of these. But in this case, would the top give you any critical points? No. Would the bottom? Yes. And what would that give you? X equals 1, right? So that's a critical point. So then how many intervals? 2 intervals. So 1 from negative infinity to 1. 1 from 1 to infinity. And I'm working in the first derivative portion. So where am I going to plug back into? The first derivative. And what information is that going to give me? Whether the slope is positive or negative, right? First derivative tells you slope is what I'm like trying to hammer in your head. So plug in 0. 0 minus 1?
Negative.
Negative squared?
Positive.
Positive. Negative divided by positive? Negative. So f prime of x is negative, which means f of x is decreasing. Alright, 1 to infinity. Plug in, it's not going to matter because of the squared. But let's say plug in 10. 10 minus 1. Positive, squared, positive, negative divided by positive, negative. So f of x is decreasing both times. Are there any relative maxes or relative mins? No. Even if it did switch, could there be any relative maxes or mins at x equals 1? No, because it's vertical asymptote. So you can't have a point on the vertical asymptote. So that wouldn't work. What am I gonna grab?
No, she's saying this one with the asymptote. So it should be like this.
Oh, so with an asymptote, what increasing decreasing look like? Maybe like that. Fair.
Just don't meet.
They wouldn't meet, and there'd never be like a point where you can say that's the relative max, because there's that asymptote in between.
So you should look to see if there's an asymptote.
When he asked.
Hold on a second.
Because, like, we have the growth, so it's over with.
Yeah.
If you don't have the growth, you should start the profit looking to see if there's an asymptote.
So what'll start to happen is you would go through and you'd say, okay, there's a relative max x equals 2. Your next step at that point will become find the y value that goes with it, because you got to put it on this graph that we're going to make. When you went to plug back in, you'd be like, oh crap, that's a vertical asymptote. That's kind of how it normally works. I mean, you can look first too, but your process will take care of it for you. We just haven't done the whole process yet. This is just a crush. Okay. So our second derivative. I'm going to rewrite the first one, so I'm going to bring that x minus 1 back up to the top, because the second derivative is a heck of a lot easier doing it that way than doing like quotient rule and chain rule. So this would be product chain rule. So bring down negative 2 times negative 3 is 6 times x minus 1 to the negative third times the derivative of the inside, which is what? Which is 1, so it doesn't matter. So the second derivative is just 6 over x minus 1 to the third. Agreed? What do we do next? Set the top and bottom equal to 0. Does setting the top equal to 0 give us anything? Nope. Does setting the bottom equal to 0 give us anything? Yep. Gives us x equals 1. Again, they won't always be the same. They just happen to be in the two examples I went through. It might. Like, I don't know. So again, you're going negative infinity to 1 to infinity, but now I'm in the second derivative work section, so where am I plugging back into? The second derivative, and what information is that going to tell me? Okay. So plug in 0. 0 minus 1? Positive or negative? Negative. Negative to the third power? Still negative. positive divided by negative. Negative. So f double prime of x is negative, which means f of x is concave down. Let's say we plugged in like 5. 5 minus 1, positive to the third power, positive, positive divided by positive, positive, so second derivative, positive f of x, concave up. So this is what I'm talking. So is there a point of inflection?
No.
So here's how if you didn't have the graph, you would start going, okay, there's a point of inflection at, and then I'm going to start making it by the y value. So it'd be like 1, comma, I don't know, let's go back and check. Well, when I went to plug